is something, something you could draw in your sleep at this point. Here's TPP, right? Okay, it's going to go ahead and attack the ketone. Now notice the R group. The R group is just this over here. All right, so I've chosen not to draw it just so that there's less for you to copy down. But again, this mechanism that I'm showing you, the first 3 steps, is identical to the pyruvate dehydrogenase complex. It just evolves slightly differently to accommodate a different substrate. So of course it adds in, and then we do our decarboxylation. Okay? That can push the electrons onto the nitrogen. Again, we see positively charged nitrogen, we're making an electron sink. So after that, we have a substrate, and as we've talked about it, it's essentially in the aldehyde oxidation state. So if it were to attack a proton at this point, as opposed to the lipoate, it would come off to form an acid aldehyde equivalent. It would form an aldehyde. But it's going to become oxidized, and it becomes oxidized in its reaction with the lipoate. Okay? So remember, this is lipoate in its oxidized form. Okay? You can either be oxidized or reduced. So it's going to undergo a reaction where it becomes reduced. Always when you see this, think of it as a nucleophile, and you're always going to push the electrons from the nitrogen, and then the pi bond is going to attack, in this case, a sulfur. We've also seen it, as I mentioned, attack a proton. We've also seen it attack an aldehyde. It always attacks something that's electrophilic. So at this point now, you've broken, okay, the disulfide bond. What you're going to do now is regenerate the TPP. How do we do that? Pretty easy. All we need to do is abstract the proton from the OH. Those 2 electrons are now going to form a pi bond, and instead of having 5 bonds to carbon, we're going to kick out a good leaving group. And the good leaving group in this case is the TPP. Okay? So after it kicks out, here's our TPP. I can then go react with another starting material substrate. So now remember, at this point, now it's essentially a transviolation reaction. Okay? We have our acylated lipoate, okay, so it contains the acyl group, and now we're going to transfer that to CoA. And that's just going to be pretty simple. We can imagine it occurring by a base removing a proton from CoA. The CoA attacks the carbonyl carbon, forms a tetrahedral intermediate, which can then collapse with protonation of the sulfur to form our reduced lipoate and our CoA substrate. Okay? Now at this point, the mechanism isn't over, right? So what will this reduced lipoate react with? Anybody remember? Think PDH complex.
FADH2.
Close. So FADH2 is in the reduced form. So it's going to react with the oxidized form. So here's our reduced form of lipoate. So it's going to now transfer 2 electrons, okay, to FAD. So you don't have to show me those mechanisms. I just want you to understand that the FAD and AD plus are still involved in this mechanism because they're involved in generating the reduced form and converting it back to the oxidized form. So the reduced form will transfer 2 electrons to FAD to form FADH2. And then FADH2 is going to transfer 2 electrons to NAD plus to form NADH. And then NADH can go off into donate those electrons into the electron transport chain to form ATP. Identical mechanism to the pyruvate dehydrogenase complex, just different substrate. All right? So hopefully by this point, TPP is one of these enzyme cofactors that you're pretty comfortable with